Okay, some general concepts here. Let's start with the definition. Stoichiometry is the skill of predicting the amount of product that can be produced or the amount of reactant needed to produce a desired product. That's chemical math. And so you can kind of think of this like making a cake. Let's say that your mom sends you to the store and she says, I want you to get the ingredients for 2 cakes. And so you read on the cake mix that you need 2 eggs and a cup of milk. And so you're going to, for 2 cakes, you're going to need at least 4 eggs, and you're going to need 2 cups of milk. Well, you would get a half gallon of milk, or maybe a quarter gallon of milk, and a half a dozen eggs. And so you're going to have some milk and eggs left over when you make your cake. And so this is some of the types of calculations that we can make with chemical equations and being able to convert from mass to moles. And so we're going to put those together so that we can figure out how much product that we can make, how much of the leftover reactants that we will have, or if we're short on something, when the reaction will stop. And so as we go along, this sounds really complicated, but we're going to lead you through it step by step, and you'll be an expert by the time we're finished. Okay, let's talk a little bit about the tools we'll need. We already have all the tools, we just got to put them together. You'll need to be able to convert moles to grams, or grams to moles. We covered that in the last unit. You'll need to be able to predict products and balance equations. That's in the unit before the last one, in unit 7, chemical reactions. And so you already know how to do that. And then you'll need to be able to use the chemical equations to make conversions. And you already know how to do that. You just don't know you know. So we will go over that, and not to fear, we're going to teach you everything that you need to know to be successful. Okay, so we are going to do some of these conversions, and we're going to start with the easiest type. And I always think that it helps to have a flow chart before you start these things. I think if you refer to the flow chart, it will help you from getting lost or confused about what kind of problem that you have. And so let's take a look at this flow chart. It may look a little bit familiar to you because we've already converted grams to moles, right? And in the last unit, we went from moles to particles. And so in this unit, we're going to be going from grams to moles, and then we're going to use the chemical equation to change from one chemical quantity to the other, and then eventually we'll turn those moles back to grams. So from grams to moles, just like before, we're going to use a molar mass off the periodic table. But when we change from moles to moles, instead of using the periodic table or Avogadro's number like we changed to particles before, we're going to use the balanced equation in the coefficients to change chemicals from one chemical species to the other. And then once we get to moles, then we can do a number of different things there. We can change it to grams, or in the next unit, we'll talk actually about changing those moles into volumes of gases as well. Okay, so we're going to start with these moles to mole type of conversions. And our first problem here says how many moles of carbon dioxide can be produced from the complete combustion of 20 moles of octane. All right, so you'll notice here that we will need to write a balanced equation before we can even start. In the problems that I give you in your worksheets, I have done this for you, but I thought it would be a useful exercise to review those skills that we learned back in Unit 7. So let's do that. We will write a balanced chemical equation. So how many moles of carbon dioxide can be produced? All right, so that's going to be a product from the complete combustion of 20 moles of octane. So we've got octane first, C8H18, and to combust anything, you need oxygen. And it tells us that we're going to produce carbon dioxide, and our other product is always going to be water in a combustion reaction. So now we have our skeleton equation, one that is not balanced, and we will balance the equation. Remember, in combustion reactions, we always balance carbon and hydrogen first and leave oxygen to the end. So if we have 8 moles of carbon on the reactant side, we'll need to put 8 here to get us started on our product side. If we have 18 moles of hydrogen in the reactant, 9 times 2 will give us 18 moles of hydrogen here. All right, so we've got hydrogen and carbon balance. Now we need to work on our oxygen. So we have 8 times 2 is 16 oxygen atoms in carbon dioxide, and we have 9 oxygen atoms in our water for a grand total of 25. All right. So there is no whole number that we can multiply by 2 to get to 25. And so we're going to use our fraction trick that we introduced in the last unit here, and we'll put 25 over 2. Now, if we could leave it like that, it would be balanced, but you need a whole coefficient number. So to get a whole coefficient number, we're going to multiply through by 2 everything to get whole numbers. And remember, if there's nothing there, it's assumed to be 1. So 2 times 1 will give us 2. 2 times 25 halves will give us 25. 2 times 8 will give us 16. And 2 times 9 will give us 18. And so now we're balanced. We started off with a pretty hard one, didn't we? Okay, but you can do it. All right, so now we know we're solving for moles of carbon dioxide, and we're given 20 moles of octane. I always like to write it above my chemical symbols to kind of keep me straight so I don't grab the wrong coefficient when I'm going from moles of one thing to moles of the other. And it's a moles to moles type of problem. So for moles to moles, we only have one step or one conversion. So let's write down our 20 moles of octane, and we're going to have one conversion. We're going to change one chemical to the other. I'm trying to color code this for you to make it a little easier to see. So we have just one conversion. What goes on the bottom of our conversion factor? Well, whatever we're starting with, right? So moles of C8H18 will go on the bottom. And what are we solving for goes on top, which is the moles of CO2. So when we got moles to moles here, moles to moles, we use the balance equation and the coefficients off that balance equation. So what goes next to the CO2? Well, 16 goes next to that one, right? And what goes next to the octane would be 2. So now we have 20 times 16 divided by 2. And I get 160 when I did that. So you would end up with 160 moles of CO2. The moles of octane cancel out, and we're left with moles of CO2. And that's what we were asked to solve for. That was our X. So we're in good shape there. All right, so let's think about that number for a minute. We've got 20.0. So there's 3 significant figures. Our answer here as written just has 2 significant figures. So we are going to have to write that in scientific notation to get our 2 significant figures. So it would be 1.60 times 10 to the second moles of carbon dioxide. All right. Very good. Very good.